Good evening and good morning, Huskies. I hope that this particular video finds you healthy and safe and finding some way to make the best out of this pandemic time. I like to think that maybe this particular pandemic could have been foreshadowed many years ago, back in the 90s. And here's entertainment to help you get through 11.3 today with a smile on your face.
Accept the fact that this city is headed for a disaster of biblical proportion.
What do you mean, biblical?
What he means is Old Testament, Mr.
Yes.
Mayor. Real wrath of God type stuff.
Exactly.
Fire and brimstone coming down from the skies. Rivers and seas boiling.
40 years of darkness, earthquakes, volcanoes.
The dead rising from the grave. Human sacrifice, dogs and cats living together. Mass hysteria.
So my point is that it really could be worse, couldn't it? Well, hopefully that'll get you smiling just a little bit. And the first thing we're going to talk about today is finding your limits, people. Just finding some limits today. So the first thing we're going to tackle today is whether or not you can determine if these limits up here at the top are continuous or discontinuous. So I'm going to give you a chance to work on these three problems to get yourself started. And then I will kick it off and figure out whether or not you know anything about limits at this point in time before we have our discussion. So give them a try. All right, so here's our answers for the first three questions up in the review. And let's just kind of take a talk about what we're really trying to decide whether or not we can say these are discontinuous graphs or not. Well, the first one, we have a binomial over a trinomial, and the first thing I did was I factored the two, and it turns out that the two of them factor out where one of the two pieces cancels out. Now, if we remember back from Algebra 2, that particular case means that there's a hole at that location. It's not necessarily an asymptote, but it's a hole that's taking place. And the first rule of our discontinuity, remember there are three rules to decide if we have a discontinuity or not. A 3 doesn't work. It's an undefined idea, and therefore that is a discontinuous graph just because of the one singular hole. Okay, second one. I pointed out that cosine is a continuous graph, as we realize it's a wave, just keeps on going forever, covers all the domain. But the problem is that the bottom of this denominator can't be 0. Otherwise, it would be undefined. And again, it violates that very first rule that it can't be exist at 0, and therefore the graph would be considered discontinuous. And the last one, f of x is equal to the square root of 2. We always worry about square roots, but I would worry about square roots if there was a variable in there. The square root of 2 is just a number, as I pointed out right here, and we're really just saying y equals 1.414, which would be a flat line, and that would cover all the domain. It would have a limit from the left and the right that would both agree that that value would be the same, and those two values agree, and that gives us the answer that it would be a continuous graph. Now, what I'm doing here is I'm really looking at these three rules that we discussed the last time I talked to you guys. Whether or not the domain, whether or not the domain is defined at every single A along the deal. So that's number one. You got to make sure that f of A is existing. Whether or not the limit exists for that particular spot too as well. Make sure that you're checking things like left and right to decide if they agree on the both scenario. So be careful. Make sure you look at that. And then last but not least, the limit and the value have to turn out to be exactly the same concept. Now, this is where I'm going to stick with today in making my decisions on whether or not certain graphs are continuous or discontinuous. So let's see if we can put those to the test. Now, it says here in the set of directions that they may, in some questions, they give you the place where the function will be discontinuous. Sometimes you might have to find that discontinuity, and it says is continuous at the given value of A. So they're going to give you a value, and they're going to say, hey, I want you to check at 2 if this graph is continuous or not. Well, we're going to go right into the three rules of continuity. Number one, you have to make sure that f of A, or in this case, f of 2, actually exists. And in this particular case, it would trigger the bottom one of this piecewise graph, and it would tell you the answer is 32. So big check mark. It passes step number 1. It does have an answer at 2. Number 2, let's check to see if the limit as x approaches 2 of f of x would exist or not. Now, if I'm getting really close to 2 and I'm not really at 2, this would probably trigger the top to be worked on. So I'm really looking at a situation of x to the 4th minus 16 over x minus 2. Now, if you tried limits in the first place, the 90% rule would ask you to plug this in, and you'd realize I got a 0 on the bottom. So I'm going to have to use a 10% rule concept here and see if I can find some way to reduce it algebraically and see what's going on. Now, the cool part about x to the 4th minus 16 is it's really a difference of squares on the top, and on the bottom we have an x minus 2. Now, that doesn't look like it did much, but this particular portion is another difference of squares, and it would be continued as x minus 2x plus 2 and x squared plus 4. And I would ultimately get that over x minus 2, and I finally get a cancellation to take place. Now, once I've gone that far, I can now try the limit a second time and see if it fixed it. And the limit in this case, as it approaches, it's going to be just fine in terms of the 90% rule. I would get 2 plus 2, which would be 4, and 2 squared is 4, 4 to the 8. Oh my gosh, it's going to be the number 32. And that limit passes that test. There is a limit at that location. Now, the last part would be number 3, to decide whether or not step 1 and step 2, do they agree? And in this particular case, the two answers that you got were 32 in step 2 and 32 in step 1. And you would say, yeah, they both agree that the answer is that. It would pass step 3. And in this particular case, at 2, so I'm going to say at a equaling 2, it is a continuous graph. It connects at that particular location. And we'd say that there's some continuity going on at that spot. Okay? So remember that we're really trying to test for continuity at a specific domain. Okay, now we'll try it again. A equals 3. Is that going to be a continuous location or not? Now they're probably picking 3, and this is something that we're going to be doing in the future. They're probably picking 3 because in a stepwise or piecewise function, we might see that more than likely any of the discontinuities that we would run into are going to be attributed to the places where the piecewise will zip together. So that's why they're trying 3. So at 3, at a equaling 3, let's decide if it's continuous or not. Number 1, is f of 3 an answer? Well, if I tried f of 3, it would trigger the top one, which would be the square root of 3 minus 3, which is the square root of 0, and that's 0. Check mark. That's an answer. It gave us something that we wanted. Okay, number 2. What's the limit as x approaches 3 of f of x? Now, when we start doing these kinds, especially in piecewise, we're going to have to look at a left and a right concept. And we'll probably recognize that anything that is less than 3 is the left-hand side, and anything that is greater than 3 is going to be the right-hand side. So we need to come up with answers on both of these and make sure that the limit exists. But we did the left already. That was 0. And now we're going to try the right. If I plug in 3 into this one, I would get 9 minus 9, and that would be 0 as well. And check it out, the answer is going to be 0 because the left and the right agree. Check mark, the limit works. Okay, number 3, do the domain answer and the limit answer agree that the answer is the same? And in this case, 0 is 0 because of those two, and it passes rule number 3, and it would be considered a continuous graph at 3. Now, as a side note to this, a side note might say, even though we are choosing just to look at 3 for continuity, and that's right, it is continuous at that location, I would be cautious looking at this particular piecewise as a whole because this square root value would not be allowed to be able to go negative. So if you were to say, are there any discontinuities in general, I would say anything that would cause that particular side to turn into a negative would be an unacceptable answer. So I think anything less than 3, like 2.99, would be a discontinuity. No, I'm not sure about that. You'd have to look at this and decide, is the negative going in there, will it keep it positive? If I plugged in 4, no, not 4. If I was less than, it was 2. It'd be 3 minus 2 is 1. That still works. I don't know. Maybe I think it would be continuous even beyond that particular part. So you got to make sure that you're really asking a question. Is it for an all situation that we're really looking at, or whether or not we're looking at a specific value in general? Now, the reason why I bring up this all case is because in those two questions, they were asking about a specific spot. Now it's going to ask a slightly different question and say, determine what numbers, if any, would give the function is discontinuous. Now you've got to come up with the places that it's going to be discontinuous. Now, the first place I would look would be these zip together spots in the piecewise. So it's probably meaning that I probably should check to see if a of 0 is one of them and a is 2 is possibly another. Another place that you might have to look to as well is the functions themselves. Be very careful. Sometimes the functions that are listed inside here may not be continuous over all domain, and they might have their own restrictions, specifically in the domain restriction that the piecewise gives. In this particular case, that's a line. That seems like a continuous thing. A parabola, which is a continuous value as well. And even though this looks all funky and backwards, that's just a line anyways, but it has a negative slope, and that's a continuous concept as well too. So I think these two are really the only two places that we need to go for. A equals 0, let's find out. Is it continuous at that location? Well, f of 0, it happens to turn out to trigger the top. The answer would be 2 times 0, which is 0. So it passes rule number 1. Number 2 would be, what is the limit as x approaches 0 of f of x? Now, again, this is going to trigger a left and a right concept. It's going to make the left turn out to be the top guy, which is 0. And it's going to be the right, which is going to trigger the middle one of 0. So 0's right-hand side is going to trigger this one. So then that answer would be 1. And you'll notice right here that that is no-go. That is limit doesn't exist at all, and therefore it doesn't pass number 2, and this concept would be considered discontinuous at a equaling 0. Now, that's only half the problem, because you just decided, yeah, they don't zip together at that particular spot. It's a discontinuity. But you have to also check the other place and see whether or not at 2, whether or not it's discontinuous at that location. Well, let's try it again. F of 2 turns out to trigger the middle one, and 2 squared is 4 plus 1 is 5. So that looks good. We've got an answer at that spot. The limit as x approaches 2 of f of x is again going to trigger a left and a right concept. The left this time of 2 would be the middle. That would be the number 5. And the right would be this one, which would be 7 minus 2, using 90% rule, would be 5 as well. And the answer for both would be 5. It would be this particular answer going in there. Now, we did good. We passed the middle rule. Third rule, do the two of them agree? And they do in this particular case. So passes rule number 3. And you'd be able to say with a degree of certainty that at 2, it is a continuous graph. And it does connect at that location. Okay, notice I didn't have to draw a single thing. Just a couple of quick tests would make a determination if the graph is continuous or discontinuous at those locations. Okay, now let's try a couple more down here, number 4 and number 5. Well, what locations seem like the most likely to be discontinuities? Well, it seems like a equaling 0 seems like the place where it could be a problem. Another problem might also stem from one of the solutions in here. 3 happens to be a flat line, so that seems continuous. Sine is a continuous graph, so I don't see any problem with that, but the 0 on the bottom there may end up being an issue, and I'm already covering it by checking 0 in the first place. So a equaling 0. Well, f of 0, we'll try the very first rule, turns out to be sine of 3 times 0 over 0. And I'm sorry to say, but that is like 0 over 0. And that's a big problem. That's the 10% rule that's kicking in here. Now, the 10% rule would mean that the three rules would be I'd try to factor it, I would try to conjugate it, and so forth. And I'm like, man, no, none of those rules really seem to work. Well, when you are stuck, you run home to mama and you put this one in a table. Okay, now in that table, you might be able to get some indication of whether or not it has a limit at all. Not a limit. Whether or not it exists at all. Wow, I was doing step 2. Sorry, that's a step 2 concept. I'm going to check to see if the limit as x approaches 0 does exist or not. Okay, I'm doing step 2. Let me do step 1. Does f of 0 work? And oh, f of 0 is 3. That one does work. I'm going to check that mark. I'm doing it backwards. Okay. Now I am checking the limit in this particular case. Let's look at the table to decide whether or not it works or not. So the first thing I would suggest you do is you would put the function itself right here in y equals sine of 3x divided by x. Okay, that seems reasonable. And not so much the graph of this, but it's going to be the table set of this. And I want it to start at 0. Check it very closely on either side. And if I look at the table on this, I'd be looking at a left and a right concept on this. And they look like the two of them, left and right, are both going towards 3, so the answer would be 3 for the limit. Okay, so some very dicey things going on there, and the only way to really get any indication of what's going on would be the fact that it's getting really close to 3. Now, answer 3 for the limit, answer 3 for f of 0. Third rule, 3 is equal to 3 in this case, and it passes the third rule, and ultimately that is considered a continuous graph of at 0. It happens that 3 turns out to be a solid dot that connects the two things together and fixes the problem. And it is continuous at that location. Now, let's try I'm not going to try to do it out of order again. Darn it, man, that scared me a little bit. Probably 3 is the one that we would like to try. So f of 3 would trigger the upstairs one, and that answer would be 4. All right, passes the first rule. Number 2. Does the limit as x approaches 3 of f of x exist or not? Well, again, a left and a right rule on this limit would mean that the top being left would be 4, and the bottom being right would be 3 squared is 9, 9 minus 3 is 6, and check it out, those two don't agree, the left and the right, what the answer is. So it fails rule number 2, and ultimately would be discontinuous at that particular location. So the whole synopsis based on this is really you've got to come back to these 3 rules that are stated about limits before you make a determination of whether or not this particular graph is continuous or not. So remember, check all of its domain, then check to see whether or not the limit exists, and then last but not least, does the limit and that particular domain agree on the answer? And if it does, then that particular deal is okay.